Good evening, class. We are looking at Module 5, covering chapters 10, 11, and 12. Here's the practice test for chapter 11, goodness of fit and contingency table. So in this case, goodness of fit test in multinomial experiments. Here are the observed frequencies from 4 categories, 5, 6, 8, and 13. At 0.05 significance level, test the claim that the 4 categories are all equally likely. As you know, we have a few steps. We want to state the null and alternative hypothesis. What is the expected frequency for each of the 4 categories? What is the value of test statistic? We want to find the critical values. We want to make a decision. So we're going to go through every step. So first, let's look at the definition. Would you be kind enough to read this for us, please?
Sure thing. Definition. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. Goodness of fit hypothesis tests are always right-tailed. If the sum of these weighted square deviations, chi-squared equals
summation of O minus E quantity squared over E,
is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the chi-squared goodness of fit test is always a right-tailed test.
Excellent. So let's see what we are going to look at here. And this was a short synopsis and definition of a goodness of fitness. So equal frequencies, as it is the case here, n divided by k, or we have E equals n times p, the proportion. As you can see in this example, we want to add up the observed values that are 5, 6, 8, and 13, and divide by the number of categories, k, which is 4. This results in 8. Therefore, we are dealing with a multinomial experiment where k is the number of categories. For us is 4 here. Alpha is given as a 0.05, and therefore we use a goodness of fit test. Each expected frequency that we calculated is 8, thus satisfy the requirement of being a value of at least 5, because if expected count is less than 5, the result of chi-squared test will not be accurate. By the way, we normally go with a right-tail test. I will explain it if we want to go with a two-tail test, what happens, but normally it's a right-tail test. So let's see what we need to do. First, the question and the fact that equally likely. You're going to write, in this case, there are 4 categories, therefore P1 equals P2 equals P3 equals P4. If you recall the concept of proportion, in this case, we have 4 proportions, and at least one of the probabilities or proportions is different from the other. This, we go with the right-tail test. And what's important to understand, they don't have to be equal. In this case, it is equally likely. What is important, they must add up to 1. All probabilities or percentages or proportions must add up to 1. The next step is to calculate the test statistic. Chi-squared is the summation of the observed value minus the expected value squared divided by E. And for us, we calculated the E to be 8, so 5 minus 8 squared, 6 minus 8 squared, 8 minus 8 squared, plus 13 minus 8 squared. Again, we have only 4 pieces, so it makes it reasonable to do it by hand. Mostly these are done by technology. When you do the math, we end up with 38 over 8 or 4.750. The critical value comes from the choice of alpha, which is 0.05. Degrees of freedom is the number of categories, which was 4, or k minus 1, that is 3. And if you look up this table, we are looking at, on the left column, degrees of freedom is 3. Up here, we have alpha of 0.05. Putting them together, the answer is 7.815. So when we do the drawing, chi-squared equals 7.815 is the critical value. The number, which is the test statistic 4.750, it's way into the non-rejection region. It's not in the tail. Therefore, don't reject H0 or fail to reject H0. If we fail to reject H0, the claim is sitting next to H0 becomes true, then there is sufficient evidence to support the claim that the 4 categories are all equally likely. If by any chance we want to go with the two-tail test, then alpha of 0.05 divided by 2 becomes 0.025. We have 2 tails. Each one is 0.025, which means this is 0.025 on the right side. And again, in order to read a chi-squared, you need the area to the right. So if you happen to have this portion and this portion, you have to read the area to the right. For this one is 0.975. So we have those 2 values. And as you can see, the value of test statistic, it is still between the 2 numbers, a non-rejection region resulting in the same value. However, let's look at the calculator result. If we were to do use TI calculator, we do goodness of fit test. So we edit and clear the 2 lists, L1 and L2. Into L1 goes 5, 6, 8, 13, the observed values, and into L2, the expected values. All of them are 8, because sometimes expected values may not be. If they are not equally likely, we will have different values here. That's why in this case there are 4 of them. All of them are equal to 8. And so if you go to stat test chi-squared GOF, goodness of fit, GOF, goodness of fit, plug in degrees of freedom and calculate. This is what you get, and let's observe what we have. First of all, 4.75 was calculated here, so that's your test statistic. Secondly, here's the p-value, which is 0.191, way larger than alpha of a 0.05, and the same decision. Fail to reject H0 or don't reject H0. By the way, fail to reject is normally a better way to write that in case. So you can write fail to reject instead of don't. All right, here's another example. Could you read this question, please?
Sure thing. Goodness of fit test in a multinomial experiments. A professor asked 40 of his students to identify the tire that they would select as a flat tire of a car, carrying 4 students who missed a test, an excuse. The following table summarizes the result. Use a 0.05 significance test to test the claim that all 4 tires have equal proportions of being claimed as flat.
Perfect. So we are using a certain formulas. Again, this is the table that is given. Left front, we're going to use capital L, capital F. Right front, lowercase r, capital F. Left rear, both of them capital, and so on and so forth. So I've explained it here because when I write the H0 and H1, it makes it easier. The numbers selected are 11, 15, 8, and 6 by the 40 students. So that makes it 4 categories because we have 4 different tires, and the degrees of freedom is k minus 1 or n minus 1. K is the number of categories, and E is n over k summation of O over k. So let us start writing. First and foremost, we have 40 students divided by 4 number of tires. So, or n times p, each tire has a probability of a 1/4 or 0.25, so times 40. Either way, we end up with the expected value of 10. Again, we expect each tire to have a probability of 1/4 or 0.25 or 10 observations out of 40 to have been a flat tire. Therefore, we are going to write that each expected frequency or 10 does satisfy the requirement of being a value of at least 5. H0, the probability for each tire, we are using capital L, capital F, which means left front, lowercase r, uppercase F means right front, and so on. They are all the same, meaning they are equal to 0.25, and at least H1 or HA, at least one of the proportions is not equal to 0.25, which really makes it a two-tailed test, but we approach it as a right-tailed test because of the limitation of chi-square. So the next step is to calculate the test statistic. Chi-squared is summation of O minus E quantity squared over E. And again, it's a small number of categories. K is only 4. So we are going to simply put 11 minus 10 squared plus 15 minus 10 squared, so on and so forth. 8 and 6 also divided by 10. And by the way, again, it's important to know that the expected value is the same for all of them. They don't have to be, which would give us, for example, 4 different fractions, not the same denominator if they are different. So you calculate that, you end up with 46 over 10 or 4.6. So that's the test statistic. The critical value comes from the choice of alpha of 0.05. Degrees of freedom of k minus 1 happen to be the same as the previous example. 4 minus 1 is 3. And therefore, we have the same chi-squared value of 7.815. If we look at the graph, here's the critical value. The test statistic is way into the non-rejection region. So fail to reject H0 or don't reject H0. Again, if you happen to have a choice of don't reject and fail to reject is a better choice. So don't reject or fail to reject H0, which means the claim becomes true. There is sufficient evidence to support the claim that all 4 tires have equal proportions of being claimed as flat. Now, if we use a two-tailed test, again, we get those critical values. Clearly, this test statistic is between the two, which puts it in a non-rejection region with the same result. Therefore, when 4 students identify the flat tire, it is not likely for all to select the same tire. All right, here's the test of independence using a 0.05 significance level. We want to test the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or girl. And here's the given information. The expected frequency is calculated as a row sum times column sum over the grand total. So we write the total here, meaning we add these two numbers, we add these two numbers, we add these two numbers, we add these two numbers. So we are adding the columns. We're going to do the same thing to the rows. We're going to add them up. This is considered the grand total. So for example, the first row, here's the row sum. The first column, here's the column sum. This number, whether you add these two numbers or these four, gives you the same answer, and that is the grand total. Use the formula to find the expected frequencies for the upper left-hand cell. So we want to use this for this number, 332. What is the row sum? 706. So we want to use it for this one. I'm going to show you one, and then all of them are calculated in the same manner. So for this cell, I'm going to go with 706, the row sum, times 1692, the column sum, divided by 2223, the grand total. Put it into a calculator, and it gives you 537.360. Of course, the number of people has to be rounded to a whole number, which becomes 537, but we want to keep it as 537.36 for the sake of better calculation. Using the same procedure, the table of expected value is calculated as follows. So we did it for one, we can do for each and every one of them. So for this one, the expected value is what we just calculated. The same thing for this one, this one, this one. All of them, we have to do the calculation. Now comes the important things. So what? What does it mean when we calculate the expected value and the expected value table? Would you be kind enough to read this interpretation?
Sure thing. Interpretation. To interpret this result for the upper left-hand cell, although O0 equals 332 men survived, we would have expected E to be 537.36 men to survive if the survivability is independent of whether or not the person is man, woman, boy, or girl. There is a discrepancy between O equals 332 and E equals 537.36, and such discrepancies are key components of the test statistic that is a collective measure of the overall disagreement between the observed frequencies and the frequencies expected, with the independence between the row and the column variables. To interpret this result of the lower left-hand cell, we can say that although O equals 1,360 men actually died, we would have expected E equals 1,154.64 men to die, if the survivability is independent of whether or not the person is a man, woman, boy, or girl.
Perfect. That's the idea to understand. Based on what we know, for example, as we look at this table, 332 men survived. Based on this calculation, if everything was independent, we would have expected a lot more, 537.36. That's the concept. How many died? They actually, the number of death for men, 1,360. It should have been less. It should have been 1,154.64, again, if they were independent. That's the meaning of that. Also, I want you to notice that as we add these two numbers, we get 1692. If we add the expected values, we also get the same values. The summation of E in rows and columns are consistent. Example, column 1. If you add these two numbers, 537.36 and 1154.64, you also get the same number. Same thing for the row. So let's look at the definition again and understand what's going on. Contingency table. A contingency table or two-way frequency table is a table consisting of frequency counts of categorical data. That means qualitative data corresponding to two different variables. One variable is used to categorize rows and a second one to categorize the column. So I want to give you the synopsis of the goodness of fit, and we continue finishing the same question we were looking at. When data can be tabulated in table form in terms of frequencies, several types of hypotheses can be tested by using the chi-square test of independence of variables. In a test of independence, we test the null hypothesis that in a contingency table, the row and column variables are independent. That is, there is no dependency between the row variable and the column variable. The test of independence of variables is used to determine whether two variables are independent of or related to each other when a single sample is selected. In this case, the sample refers to the people in Titanic. Tests of independence are always right-tailed tests if the sum of this weighted squared deviation, summation of O minus E quantity squared over E, is small. The observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the test of independence is always a right-tailed test. So to continue with the same question, we have the table, we have the expected values for each cell, and let's look at the requirement. Let's assume random selection. Results are frequency counts. And the expected values, as you can see, are way larger than the 5. So, step 1, H0 and H1. Whether a person survived is independent of whether the person is a man, woman, boy, or a girl. Or in short, the row variable is independent of the column variable. And that is the claim. That is the one that we are checking. H1, surviving the Titanic and being a man, woman, boy, or a girl, is dependent. Or you might say the row variable is dependent or related to the column variable. So there are a couple of different ways, and you don't have to go with both, but understand that there are variations of that. So test statistic, summation of observed value minus expected value quantity squared over E. So for example, if you look at this one is 332 minus 537.36 quantity squared and then divided by 537.36. You go all the way to the end, you do the same thing for each cell. Look at the last cell, 18 minus 30.36 709 quantity squared over 30.709. So that's what I was referring to when the denominator, they are not the same. And so putting it into a calculator, which will result in 507.084. The next step, what is the degrees of freedom? Degrees of freedom is R minus 1 times C minus 1, the number of rows minus 1 times the number of columns minus 1. So we have 2 rows, so 2 minus 1, and 1, 2, 3, 4 columns, 4 minus 1. Not the total. The total does not count, okay? So therefore, we have 1, 2, 3, 4 different categories here, 1, 2 different categories here. 2 minus 1, 4 minus 1 is 3, alpha is 0.05. And the critical value is chi-squared equals 7.815. And when we go with the graph, 7.815 is somewhere here. And this number, which is a test statistic, is way larger than 7.815, the critical value. It's way into the rejection region. Therefore, you are going to reject H0 or the claim that says the row variable is independent of the column variable, and you would write the decision, reject H0. The claim is false. There is not sufficient evidence to support the claim that when the Titanic sank, whether someone survived or died is independent of whether the person is a man, woman, boy, or girl. Survival, this is another short version. Survival and gender are dependent. That's what we have proved. Needless to say, this is basically done by technology. So first you access the matrix. If you go with TI, it's the second, and x to the power of negative 1, the inverse, and you edit. So matrix A, if we go back to this one, the number of rows first is 2, the number of columns is 4, and you put the numbers 332, look at that, 318, 29, there's no room to show the next one. This one is 1,360, the next one is 104, the next one is 35, and there's not enough room. So this is matrix A. Then what you do, you use stat test and you look at chi-square test. When you go to chi-square test, it gives you automatically the observed value, and that's the observed value A. Then it creates an expected matrix B. All you have to do after you enter this one, say calculate. When it does that, it gives you those values. Let's see what they are. It also creates the expected frequencies and puts it in matrix B. If you look up matrix B, you can see, for example, 537 point with a lot more decimal than what we have here. But if you look at the next one, 1,154.64, again, with a lot more decimal, and so on and so forth. Meaning, if you plug in matrix A, if you do this, after you get to here, you also see the B matrix, which is the expected frequency. You don't have to do anything by hand, but you need to understand the concept. Now, notice, this number that we calculated by hand is the same as here. Of course, this is having more decimals. If we go with the second one, they both end up being 507.08. So we didn't do it too bad. So it was very close. P-value is 0. And when the p-value is 0, of course, it's less than alpha, and you reject H0. As far as the p-value, normally you bring it from the technology. However, if you go with the table, this number is not there. The highest value is this number from the table. So p-value is way less than 0.005, and alpha is 0.05. So since this number is way less than that, you reject H0, but of course, technology will do the job. So p-value is 0, way less than alpha 0.05, reject H0 if you want to go with the p-value. Test of homogeneity using the following table with a 0.05 significance level. Test the effect of a pollster gender on survey responses by men. So we have men who agree, men who disagree, and the gender of interviewer. They are either men or women. So when there were men who agree were 560, but in the case of being women, the interviewer, then the answer changed to 308, so on and so forth. That's the meaning of this table. So we have two categories. One category is the gender of the interviewer, and one category refers to the gender that is being interviewed. One is those men who agree and those who disagree, same gender. And so let's look at the synopsis of chi-square test of homogeneity. Could you please read this?
Test of homogeneity of proportions is a test of the claim that different populations have the same proportions of some characteristics. The test of homogeneity of proportions is used to determine whether the proportions for a variable are equal when several samples are selected from different populations. Test of homogeneity are right-tailed if the sum of these weighted squared deviations is
summation of O minus E quantity squared over E
is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the test of homogeneity is always a right-tailed test.
Excellent. Basically, the test of homogeneity is the same as the test of independence. The only difference is that in the test of independence, we are dealing with one sample, but in the case of homogeneity, test of homogeneity, we pick it up from different populations. Other than that, it's the same. So let's move on. We are going to do the same thing as we did before. So we are going to add up the columns. We are going to add up the rows. And when we add these two numbers or these two numbers, we get the grand total. So it's very similar to that, as you can see. And E is row sum times column sum over the grand total. So the table of expected values, so this table along with the expected values, and we see them in highlighted format instead of 560, for example, the expected value is 578.67. And how did we calculate that as an example? Then we go with the formula row sum. In this case, the row sum is 868 times column sum, in this case is 800, and then divided by the grand total of 1200, and that results in the number that you see here. Again, just as an example, if we can calculate one, we can calculate all. So the requirements are checked. Based on the description of this study, we will treat the subjects as being randomly selected and randomly assigned to the different categories. The results are expected as frequency counts. The expected frequencies are all at least 5. As you can see, they are all larger, way larger than 5. So let's repeat the table here and actually write the steps. Step 1. H0, the proportion of agree-disagree responses are the same for the subjects interviewed by men and subjects interviewed by women. In other words, P1, P2, P3, all the way to P sub n. In this case, there are 4 of them, okay? So you can stop at P sub 4, but just in general. They're the same, or Survey responses by men are independent of poster gender. You can even write it in this manner. Although it's test of homogeneity, that's the meaning of it in essence, and that becomes a claim. H1, the proportions are different, or you can write the whole thing. Or at least one proportion is different from the other. Or you can say survey responses by men depend, instead of independent, depend on poster gender. So there are a couple of different ways. In this case, I put them in 3 different ways. You don't have to write all of them, but you need to understand what they mean. So however they give it to you, you should be able to distinguish among those. So let's calculate the test statistic summation of O summation of O minus E quantity squared over E. By the way, this is capital sigma, which represents summation. So for example, 560 minus 578.67 quantity squared divided by 578.67 plus 308 minus 289.33 quantity squared divided by 289.33 all the way to the end. And I am writing also the last one, 92 minus 110.67 quantity squared over 110.67. You put it into a calculator, you end up with this number. The next thing is degrees of freedom is R minus 1, C minus 1. As you see, we have 1 and 2 columns. The total doesn't count. We have 1 and 2 rows. So 2 minus 1 times 2 minus 1. Degrees of freedom becomes 1. Alpha is 0.05. The critical value, 1 alpha, becomes 3.841. If we do the drawing, 3.841 is the critical value, and the test statistic is way into the rejection region inside the tail. Therefore, you reject H0, which means you're rejecting independency. And therefore the claim becomes false, and we write it as follows. Reject H0, which means we are rejecting independence. The claim is false. There is not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. Another way of putting it, there is sufficient evidence to reject the claim of equal proportions. So please pay attention to the way we write it. There is not sufficient evidence to support the claim, or there is sufficient evidence to reject the claim. Also, you can write survey responses by men depend on poster gender. You can look at it that way. And again, this can be done as we did it with technology. If we go with two-tailed test, the chi-square root of the left is 0.001 and the right is 5.024. As you can see, this number is larger than both of them. It's way into the rejection region, even in the case of a two-tailed test, and we get the same result. All right. Let's look at the last question. Test of homogeneity using the following table. With the 0.05 significance level, test the association or dependency or relation between people living in a city versus outside and becoming infected with a highly resistant bacteria. So here's the bacteria condition. We get either infected or not infected. So that's the case. Let's go through the process. H0, whether a person is infected, is independent of whether the person lives in the city or outside the city. That means they have the same proportions in essence. Whether a person is infected is dependent of whether the person lives in the city or outside the city. So it's either independent or not dependent, and we go with the right tail test. Let's do the calculation here. This is chi-squared, is summation of observed value minus E quantity squared over E, and the degrees of freedom are -1 times C -1. So Again, if you were to do it by hand, you would add up these two, you would add up these two, you would add up the columns, and this is the grand total. So just as an example, for this one, for this cell, we would multiply the row sum by the column sum divided by the grand total. So 10,162 times 17,139 divided by 40,048, and it results in 4,142.088. If they are independent, that is the expected value. So you calculate that for everything, for every cell. And now there is another way of making this easy, if especially you're using technology such as Excel. You can calculate this O minus E quantity squared over E per cell. So if you do that per cell, it gives you those values. So you can either write here in this format, for example, for this one, is 4,239. I'm looking at this cell that we did the calculation, minus 4,142.98, square that, and divide by this number, 4,142.088, and go with the rest of them as well. This is done here in essence. O minus E, quantity squared divided by E, and when you add them all up, or this one gives you 5.047424. The next step is to find the critical value. Degrees of freedom is R minus 1, C minus 1. You have only two columns, two rows. So 2 minus 1 times 2 minus 1, that's 1. Alpha is 0.05. Remember, most of the time it is 0.05. The critical value becomes 3.841. We have seen it. And therefore, if we go with the graph, this number that is calculated as a test statistic is way larger than the critical value of 3.841. It puts us way into the rejection region. Therefore, we are going to reject H0. We are going to reject independence. Also, this comes from technology, everybody. This comes from technology. And it has the value of test statistic. It has the critical value, of course, with a lot more decimals. And it does have the p-value of 0.0246, which is clearly less than 0.05. And the result is the same, reject H0. So let's go over that. Reject H0, that means reject independence. The claim is false. There is not sufficient evidence to support the claim that whether a person is infected is independent of whether the person lives in the city or outside the city. So another way of putting it, whether a person is infected is dependent of whether the person lives in the city or outside the city. That's the same way of putting it. And the p-value, according to this, is 0.025 less than alpha, which results in the same thing. And as I mentioned, this comes from technology, everybody.